Okay, in this video I'm going to show you an example problem that deals with a traveling wave. And this is actually a digital signal, so this is a digital signal problem. And we're given the bit rate and we're given the propagation speed of the signal. And it asks us to calculate the bit period in a couple different units. It actually asks us to calculate the length of the bit on the wire, and also the time to transmit a certain number of bits. And we'll do this by starting with the quantities we're given, the 5.5 megabits per second, and that is, in the notation we're using in this class, R sub B, that is the rate, the bit rate, which is 5.5 megabits per second. And I'll go ahead and notate what we're given here. The propagation speed is a script v, in my habit of writing it, 2 times 10 to the 8th meters per second. And I'm going to go ahead and calculate the bit period for part A. TB is equal to 1 over RB. Perhaps the most straightforward way of doing this is to always plug in to these equations values that are in bits per second. And take all the megas and gigas and millis and micros off of there, and mega is times 10 to the 6th. And so I can plug this into my calculator. 1 divided by 5.5 times 10 to the 6th. And I'm going to get 1.82. Let's see if I can get my calculator. 1, 2, 3, 4, 5, 6, 7 times 10 to the minus 7th seconds. Okay. And so this is 0.182 times 10 to the minus 6 seconds. And I'm turning this into 10 to the minus 6 seconds because it wants the answer in microseconds. And so this is 0.182 microseconds. And that agrees with the answer that's given in the Excel sheet that I give you guys. Okay, express the bit periods in units of nanoseconds. For part B, I'm going to go ahead and rewrite the same quantity. And notice here that I'm following the rule that if I increase this quantity, I'm going to decrease this one by the same factor. So here, from 10 to the minus 7 to 10 to the minus 6, I've multiplied by 10. Okay? Here, I divide by 10, and that keeps the number the same. Okay? And now I'm going to go into nanoseconds. And a nanosecond is 10 to the minus 9th seconds. And so if I start with 0.182 times 10 to the minus 6, that turns into 182 times 10 to the minus 9th seconds, or 182 nanoseconds. I don't know where I'm getting this 6 from here. I think I wanted to put an S there. Yeah. So it's 182 nanoseconds is the bit period. Okay. For part C, it says to calculate the length of a bit on the wire. And we have an equation for this. And basically the distance traveled, and I'm going to call it S, is equal to the velocity times time. This is a very general equation. Think of driving your car at 60 miles an hour for 2 hours going 120 miles. Okay? And what we're going to do is it asks us the length of a bit on the wire. So as the transmitter sends out 1 bit, it takes a certain amount of time, which is equal to this bit period actually. And given the speed of propagation here, we'll calculate the distance that the front of the bit on the wire has gotten. Okay, and so what we're going to do is we're going to use the V given, 2e to the 8th meters per second, and we're going to multiply that by the time for 1 bit, which is 1.82 times 10 to the minus 7 seconds. And this is going to yield a distance s in meters. Okay? And if I multiply that on my calculator, I go 2 times 10 to the 8th. 2 times 10 to the 8th times 1.82 times 10 to the minus 7th. And I'm going to get 36.4, and that has units of meters. And so I've got meters per second here, and I've got seconds here, and that yields meters. Okay. Finally, on part D, it says how long does it take the transmitter to transmit a packet consisting of 740 bits. Now this is going to use another equation which is almost exactly analogous to our distance is velocity times time, but it's going to be the number of bits is the bit rate times the time. Okay, so the number of bits is equal to the bit rate times the time. And so the units are bits, and the units over here are bits per second and seconds. Bits per second for the bit rate and seconds. And so you can see that the units do work out, and it's almost just like distance equals velocity times time. And so how long does it take to transmit? So here we're given 740 bits, so NB is 740 bits. And it wants to know how long it takes. And so I'm going to solve for t here. T is equal to NB over RB. And it's the 740 over my 5.5 times 10 to the 6th. If I plug that into my calculator, I'll go 740 divided by 5.5 times 10 to the 6th. And that's equal to 1.345, let's say. We'll just take 3 or 4 significant digits, times 10 to the minus 4th. And that's going to be in seconds. And does it tell us what units to put that in? No, but I'm going to go ahead and call this 13.4 milliseconds. Okay? And what I've done there is I've said this is times 10 to the minus 4 seconds. Sorry about that. There's my minus sign now. And if it's 1.3 times 10 to the minus 4, maybe I did that wrong here. Let me think about this. 10 to the minus 4 seconds. A millisecond is 10 to the minus 3, so I multiply by 10. I better divide by 10. It's very easy to do that. You have to double check your work on this. Let me try that again. I'm going to call this 0.134 milliseconds. And what I've done is I've gone from 10 to the minus 4 to 10 to the minus 3. Milli is 10 to the minus 3. So I multiplied by 10 here, so I better divide by 10 there. Okay, so that solves this problem. Hope that helps. And there you go.